In the last video, I showed you a data structure called a dynamic array, which is like an array, only it can expand to fit in new items. The way it works is when you add an item that you don't have space for, you allocate a totally new array, and then you copy all the old items in and then add your new one. This only happens once in a while, and so you get almost as good performance as a contiguous array, but with the kind of flexibility you might expect from a linked list. Isaac left a great comment on this video talking about what Python does and also saying that allegedly the ideal resizing factor is the golden ratio, which got me quite curious as to why that was, and now we have this video. We'll look at some of the common choices of resizing factors, some unusual ones, including some lost to time, and it's just possible we could change the world of dynamic array resizing as we know it. It's not particularly likely, but it is possible. What you're watching now is how the growth factor of 2 actually plays out in memory. The yellow boxes being our actual array, with the bright yellow meaning the actual data, populated cells, and the dark yellow meaning that it's allocated space but not yet used. Whenever we hit the maximum of a given array, you'll notice that a new array is allocated after the previous one. The previous one then turns blue, and you can see the progress as it copies items from the old array into the new one. We've also got a display on the right which shows us a few things. The array length, which is always going to go up except when we're resizing the array. The number of storage operations we've done, which is going to stand in for our sort of time complexity. And we've got 2 statistics as well. The first is the average number of operations per element appended to the array. So you can see this one is bouncing between about 2 and 3, and lower is generally better for us. The second is memory efficiency, and I've calculated this by taking the number of slots actually used for data divided by all the memory from address 0 in this diagram to the end of the last allocated address. So that's going to include all of the unused space in the array as well as all the space before it. This isn't an average and will vary a fair bit as the data moves around, so I've put an average in red that you can use to get a picture of roughly where we're at. And this one also pauses during the resizing operation to make it a bit less noisy. I'm showing you all this to illustrate a significant downside of using a growth factor of 2. Notice how this array is always moving downwards in the memory space. We can't reuse the memory space earlier because it's not big enough to slot our new array into. And with a factor of 2, it's always going to be too big. And this means, in this simplified model anyway, that we're wasting quite a lot of space. We might prefer a scheme which allows us to reuse that space somehow. And we can achieve this by playing around with the resize factor. This resize factor is 1.1, meaning the array is going to be resized to be only 10% larger each time. As you can see, the operations per element appended is now around 10 to 12, significantly higher than last time's 2 or 3. It still runs in linear time, but it's going to be significantly slower linear time. But the memory efficiency is significantly better, about 60%, and that's up from the 40% we saw with a factor of 2. You can also see that it's very regularly reusing the memory at the start of our area, which is nice. So a growth factor of 2 is efficient but seems to waste a lot of memory, while a growth factor of 1.1 is slow but seems to use memory more efficiently. So the question is there a middle ground? And it turns out that there is. There's actually a theoretically optimum number. And this number is the golden ratio, or phi. There's an algebraic way to show this, but I think it's interesting to look at it visually. Let's take this only slightly impractical scheme. Every time we resize an array, to decide its new size, we add the previous 2 sizes together. This would mean that our array resizings would form the Fibonacci sequence. In this visualization, I've highlighted the new array at the end, and then directly before it, the array we'd need to copy out of. And I've put the now free space occupied by all the previous arrays in this dark grey. Just above that grey, we've got its total size in bytes, and just below it, I've put the size of the newly allocated array just for comparison. As you see the sequence progress, you will notice that these 2 sizes get closer and closer to each other. After a few terms, they end up exactly 1 slot difference in size. Almost perfect for us to slot our new list into. Almost. Now, another way to say add the previous 2 sizes to make the next one is to say multiply the array size by the golden ratio. The golden ratio is what one Fibonacci number divided by its previous one tends towards. So if we're optimizing for memory reuse in this abstract scenario and we're going to resize arrays forever, this represents a very nearly, almost ideal scheme. We just need to make a slight adjustment to make the array just a little bit shorter. And we could do this by just subtracting 1 or we could do it by using a number just a little under the golden ratio. But handily, the golden ratio, which is 1.618 and then a bunch of other numbers, is quite close to 1.5. A ratio of 1.5 is quite easy for computers to work with, and also means we can reuse the memory a fair bit sooner than if we used a number very close to the golden ratio. So a lot of programming languages make that choice and use 1.5 as the growth factor for dynamic arrays. And here's what it looks like. And it's pretty good. In this example, we get a memory efficiency of about 50% and between 3 and 4 operations per append. To compare it to our other options, that's just a little slower than the factor of 2 algorithm, and in terms of memory efficiency, it's about 10 percentage points worse than the factor of 1.1 algorithm. Now, programming languages don't tend to specify the growth factor they use, but they tend to use either 2 or 1.5. 2 will be a little faster but potentially lead to overuse of memory, and 1.5 will be a little slower but potentially lead to better memory reuse. Microsoft's C++ compiler uses 1.5, GCC and Clang seem to use 2 everywhere, Java uses 1.5, C# seems to use 2, Python uses around 1.125 for some reason. Go starts off with a factor of 2 for small lists and then switches to 1.25 over 1,000 elements, and that's about the spread of it. How all of this plays out in the real world is hard to determine. The best empirical data I could find was when Tom Ciovoloni of the Rust team experimented in changing their vector resize factor from 2 to 1.5. They ran their pretty rigorous looking benchmarks, and all of their cycles benchmarks got worse, some of them significantly worse. The memory picture was more mixed. Most got a bit better, but some got worse and some significantly worse. And they ultimately decided against the change and stuck with a factor of 2. When I was researching this topic though, there was one other comment hidden away on a Usenet thread which caught my eye, and it proposes another approach. It's pretty weird, and I don't know enough about memory management to say whether it's definitely a good idea or not, but in my simulations it seemed strangely promising. I've not seen it talked about anywhere else though, other than this one comment, possibly because it's so strange, so we may together be about to discover the next big thing in dynamic array resizing. Probably not, but still exciting to look at, so let's do it. I'll start by reading you the comment. It's from Risto Lankinen on a thread discussing the ideal resizing factor and why Microsoft C++ uses 1.5. And I just love how this comment starts as well. It's just, you know the thread's going to get good from this point. Here we go. This is a novel idea, and I understand the underlying theory. However, according to my calculations, using a growth factor of 1.5 generates almost exactly twice as much copying than using the growth factor of 2 in the long run. However, the difference in the amount of copying taking place would allow a modification to the growth factor 2 algorithm which, after copying stuff from the old block to the new block, would free the old block and allocate yet another block the size of the new block, which will now fit in the space vacated by the old block as well. This algorithm would perform as many copies as the algorithm that uses growth factor 1.5, despite the fact that it does a redundant round of copying to compact the free store, so it would still be at least as good, but would have an additional performance benefit of being able to postpone the redundant copying until the space actually becomes a concern. So I found this a little hard to interpret. At first I thought that he must be suggesting using a resizing factor of 2, plain and simple, but that's actually just the plain old doubling algorithm, so either he's mistaken or he's got some other idea. Then I thought maybe he's suggesting doubling and then doubling again, which actually doesn't make sense or work out either. I tried both of these and a few variations, and I couldn't explain the fit in the space vacated by the old block behavior that he talks about. But then it struck me, an idea so fundamentally bizarre that I dismissed it even as I read it. I'm going to call this algorithm Lankinen's algorithm since I've never heard of it anywhere else, and he seems to have crafted it himself just for this comment. And it works like this. Whenever you need to resize, and let's say your array is of length n, you allocate an array of size 2n and then copy over the values just as before. Then you free the old one just as before. Then, after that, you allocate another array of 2n and you copy the elements over again, except this time you just copy the first half since you know the second half is empty, since you just allocated it. And that's it. You just resize the array and then copy it once. Weird, right? Seems totally pointless, and yet the result is an algorithm which uses as many operations as the 1.5 ratio and achieves the same memory efficiency, and in fact just a little bit better. And it does have another nice property too. Array sizes are always going to be powers of 2, which is nice, and this extra copy step is always optional. you might decide not to do it if you don't want to worry about memory for whatever reason. So this is starting to look pretty good. Let's look at all the algorithms we've seen so far and try to compare them in a bigger simulation. First, let's look at a chart of the operations per second for each growth factor. Lower is faster here and thus better. It's no different than what you've seen before, and it won't change with anything we're about to look at. It's just a useful point of comparison. You want to remember that of the 4 growth factors we're looking at, 1.25 is the slowest and 2 is the fastest. 1.5 is somewhere in the middle, and the growth factor of 2 with the Lankinen algorithm is a little slower than that. Now let's look at the memory efficiency, where higher means that more of the memory we've used is taken up with our actual data. 1.25 is the best growth factor from that perspective, and 2 is the worst. 1.5 is in the middle, and our Lankinen 2 is even better than that. Note that this particular graph is affected by 2 things. The first is that the higher growth factors will always have worse memory efficiency even if we have some incredible memory packing algorithm, because when you resize an array, it's necessarily going to be half empty at the start, whereas with a factor like 1.25, it'll be quite nearly full. Smaller growth factors are more conservative in their resizes and so tend to have better memory efficiency for that reason by default. However, there's also the matter of the gaps we're leaving in memory, and this is the second thing that contributes to the score. We can break out the gaps problem to a separate graph too by just adding up the space in the gaps. Here you can see the starkness of factor 2's inability to reuse memory and just how effective the Lankinen algorithm is by comparison to all of the others. So to recap, our ideal algorithm would take very few operations to append an element, it would leave very little discarded memory, and it would have the maximum memory efficiency possible. All of these simulations came out of an average of 1,000 different simulations with different numbers of elements appended. I did the simulation this way because the efficiency of each algorithm sort of depends on exactly when you stop, and each algorithms look better at different stopping points, so I wanted to find a way to average over a number of different situations. All of this is just another way of looking at what you've seen before to make it easier to compare. But I wanted to do some more simulations, so the obvious next thing to look at would be, what if we had more than one array in the same memory space? So I wired everything up to simulate 2 arrays, picking randomly which to add to in randomly sized batches between 1 and 100 elements at a time. Here's what happened. A major upset. The Lankinen algorithm is now much worse, leaving very significant gaps in between the arrays. Even more surprisingly, the non-Lankinen 2 growth factor, the normal one we looked at first, has somehow dramatically improved its memory efficiency by somehow filling in all those gaps. In fact, the 1.5 factor has improved significantly too relative to the 1.25 factor. I was curious how this picture would evolve as you added more arrays, and so I simulated it up to 25 arrays. By the time you pass 3 arrays, most of the difference in gap filling between the different resize factors evaporates, and in fact, from then on, the resize factor of 2 actually performs slightly better. I guess because the gaps are a nicer shape to reuse. It still doesn't fully make up for the gap in memory efficiency caused by the resize factor of 2, just meaning arrays are more empty more of the time, but the resize factor of 2 is also significantly faster. All of this makes the resize factor of 2 look like a pretty promising algorithm. I'm not saying that the decision of major languages to use 1.5 as the resize factor rather than 2 was based on some lovely ideas to do with the golden ratio that don't actually pan out in reality. I'm not saying that. I don't know. All of these simulations are very limited and they may not compare to real world scenarios very well at all. All I'm saying is it could be worth looking into. I've tried out a fair few variations of this simulation now with lots of small arrays or scaling the size up, and every time it shows that as soon as you add a second array to the picture, the packing benefits of 1.5 seem to evaporate. And as soon as you add another few, the resize factor of 2 seems to pack memory even better. So it's not feeling like a slam dunk for 1.5, and maybe it's worth taking another look at. I mean, it's an important data structure after all, so it could be cool to see what would happen if we tweaked it a bit. So if you have access to some great benchmarks for the major languages of the day, and you can try it out with a resize factor of 2 rather than 1.5, I'd be really curious to know what you find. So I got to the end of making and editing this video and I realized that I'd missed a piece of the puzzle. I'd not actually properly researched where all this 1.5 and golden ratio logic came from. Maybe whoever came up with it had benchmarked it and tried loads of scenarios, and if so, I should include that in this video. So I did my research and I managed to trace it back to a paper by Andrew Koenig, a researcher and programmer who worked at Bell Labs and later AT&T. And unlike almost everyone else I cover in the history section of these videos, he's still firmly with us, which is great. Unfortunately, his paper titled Why Are Vectors Efficient is mostly lost to time, having been published in a now abolished journal called JOOP, or the Journal of Object-Oriented Programming, whose online archives are very spotty. However, with a bit of effort, I did manage to partially reconstruct it. I felt like a real historian doing this as well, trying to stitch together random pieces that got cut off in weird places. I won't tell you how I did it, but I imagine you can guess. Like so many of the classic computing papers, it reads really wonderfully. The paper is mostly about explaining how dynamic arrays, aka vectors in this paper, use exponential growth to achieve amortized constant time for the append operation, like we covered in the last video. In one paragraph, which I really enjoy, he says, "It turns out that there is a simple strategy for allocating memory for vectors that performs remarkably well. Proving that it performs well is somewhat less simple. The first time I encountered the strategy, I was surprised that it was worthwhile at all. But the strategy itself is easy to describe and implement." I just think that makes you want to read more, you want to find out. It's got that sort of technical adventure vibe, which is so much fun in these papers. But what about all the golden ratio stuff? Koenig does a great job of explaining it with all of the drama that it deserves, but he notably pulls his punches when it comes to whether we can be certain that 1.5 is the ideal factor. Here's one of the paragraphs where he's talking about that. Of course, the difference between practice and theory is greater in practice than it is in theory. For example, allocating memory usually involves some amount of bookkeeping overhead, which makes all of our equations approximate instead of exact. Nevertheless, this line of reasoning suggests that there is an advantage to choosing a value of f less than 1 plus the square root of 5 over 2. That's the golden ratio, by the way. An obvious value to choose is f equals 1.5, because it's easy to compute on a binary machine, and indeed the first variable length array class I ever wrote, more than 10 years ago, used f equals 1.5 for precisely this reason. However, I believe it would be worthwhile to do some experiments to determine the best value of f in practice, and I would like to encourage readers to do so. And perhaps later experiments were done, possibly by Koenig or maybe by somebody at Microsoft to justify the Microsoft C++ compiler change, or maybe by somebody else. But I think it's notable here that Koenig stops a fair bit short of saying this is the right number to use, and only suggests that this is an interesting argument to investigate 1.5 further, which I guess is what I've done with this video. I'll post my partially reconstructed version of the paper on the ODE's website, since I don't really think there's any way to buy it now, and it feels worth sharing as an important piece of computer science history. I'll also be doing a little talk-through video for ODE's members where I read the paper and just try and fill in some of the gaps so it makes more sense. So if you're an ODE's member, watch out for that coming into your inbox pretty soon. It's time for me to say that this video, like all ODE's videos, comes with some exercises so that you can put this into practice yourself. This one is a little puzzle which I'll talk you through now. Let's say you have a single array in a memory space which is 2 to the power 128 bytes long. That's pretty big, by the way, so this grid is only an example. You have a dynamic array of single byte values starting at 2 bytes long. Whenever you need to add an element which is longer than the size of the array you have, you're going to need to resize it up. You're going to use the resize factor in this puzzle of 1.618. And you're also going to take the ceiling of it. So if you have an array of 2 bytes long, you're going to multiply that by 1.618 to get 3.236. I'm reading that, I'm not calculating in my mind. Just in case you thought I was some sort of calculating genius, which you probably don't. And anyway, so you get that value, and then you take the ceiling to get 4, so you resize from 2 to 4. And of course, as you go up, that's going to get less power of 2z. Now, when you resize, you should place this array at the first point in memory it's going to fit. This is mostly going to be after the previous array, but sometimes, as we saw in this video, it's going to be before the previous array. Note also that you're going to need to keep the old array around to copy all of the values out of, so you can't position your new array over your previous array. Now, this resizing algorithm is going to eventually run out of memory. That's going to happen at the point where you try to add an element and you need to resize the array up, but there's no longer any free space in memory to place your new array. It's either taken up with your previous array, or the gap before or after it is too small to fit in the new size. So for this smaller example of a 384 byte long memory space, you can add 143 elements to the array before you're not able to resize it up any further and you're not able to fit any more items in it. The next size up would be 232 elements, and that doesn't fit before or after this array. So your question is, for the 2 to the power of 128 byte long memory space and a resize factor of 1.618, how many elements can you add before you run out of memory? Let me know how you get on with it. By the time you've done it, you'll have the lion's share of a simulator that you can use to try out some of the scenarios we've seen in this video, and maybe you'll discover something new about resizing factors yourself. I've also created another exercise exclusively for Odes members, who are the people who support me to make these videos. It's £10, dollars or euros depending on where you are, and for that you get ad-free viewing, plus extra exercises with every video, and projects which allow you to really test your skills which go with every season. Plus, of course, my gratitude for supporting me in this project, so thank you for that. If you're interested in signing up, you can head to the Odes website, which is linked in the description, and various buttons and links will ferry you along the way to the right page. So thank you to Isaac for the comment which sparked all of this off, and thank you to you for watching. And in case you were wondering why my hair is like this, I'm really trying to get onto the 10-day schedule because I think it's good to release things regularly. And I was, today, what was I doing? I was doing dumbbell snatches today. So it stimulated a certain amount of effort on my part. And I didn't want to wait to record the intros and outros for this video, which I like to do because I think it makes me more present, and I don't want to become a, what do they call it, a faceless YouTube channel. And I also don't want to become a YouTube channel that only releases every 6 months. So you have to put up with the hair for that. Yeah, next one, another shorter one, probably focused on linked lists. And then after that, we're going to be getting into Forth, which I'm very excited for. Yeah, that's it. Have a good day. See you later.